Hi, hello everybody. So today we have our first set of practice questions from the basics that we have already learned, quantum numbers. Okay, so there are 10 questions in this practice set. Let's try it out. So the first question is the number of orbitals in L subshell is. So by now you know that L corresponds to the azimuthal quantum number and the number of orbitals are generally represented by the alphabet M, right? So they are asking what is the relation between M and L. So let's take a few examples and then try it out. We have already discussed this in the previous session, but let's try it out. So let's say that our L value is equal to 0, which corresponds to S subshell, right? And when you have S subshell, you know that the possible values of M lies from minus L to plus L. The values of L can take minus L to plus L for the magnetic quantum number that corresponds to the number of orbitals, right? So, if L is equal to 0, S is the subshell, M can take values of 0 only. Minus L to plus L, which is M is equal to 0, right? And when you have L is equal to 1, it corresponds to the P subshell. And the possible values are M is equal to minus 1, 0, plus 1. So you have three values. And if L is equal to 2, it corresponds to the D subshell. And the possible values of M are minus 2, minus 1, 0, plus 1, plus 2. So you have to note that in between the values, there should be a unit 1 difference. Okay, so if you take 0 and 1, the difference is 1. If you take 1 and 2, the difference is 1. If you take minus 2 and minus 1, the difference is 1. Okay, so always between the consecutive values of M, there should be a difference of 1. All right. So when you have a value of L is equal to 2, there are 5 possible orbitals. Correct? Now from this, you can get a relation. So when the value of L is equal to 0, the number of orbitals is equal to 1. When the value of L is equal to 1, the number of orbitals is equal to 3. When the value of L is equal to 2, the number of orbitals corresponds to 5. And from this, it is clear that the number of orbitals is equal to 2L plus 1, right? So you can try putting it over here. 2 into 0 plus 1 is equal to 1. You have got only one orbital. Over here, 2 into 1 plus 1, 3 orbitals. Over here, 2 into 2 plus 1, 5 orbitals. Okay? So the number of orbitals in any subshell is equal to 2L plus 1. So the correct option is option C. All right. Let's go to the next question. For a particular value of azimuthal quantum number, in the question it is represented by the alphabet L, the number of magnetic quantum number values, which is again M, are given by. So the same question which was given earlier is rearranged over here, right? Now, how is it rearranged? Let's see. So earlier we saw that the value of M, or the number of orbitals in any atom or any subshell, is equal to 2L plus 1. Correct. Now we can rearrange. So here M is equal to 2L plus 1 by 2 is what is given. So option B is wrong. In all the other options, the answer is written in terms of L. So let's try and rearrange this in terms of L. So in terms of L, this is going to be equal to M minus 1 is equal to 2L. Take 2 to the side. M minus 1 by 2 is equal to L. So the correct answer is option B. Option B is the correct answer. Right. Now, again, a generalized question. Question number 3. The number of subshells in the nth shell of any atom is. Again, let's do it by examples. Let's say that your principal quantum number is equal to 1. Then the possible subshells are 1s. Correct? It can take value L is equal to 0 to n minus 1. And 0 to n minus 1 means only 0 is possible. the values of L that corresponds to the number of subshells is equal to 1. You can have only one subshell and that is 1s. Let's say your values n is equal to 2, then your values of L can be 0 and 1 because the values of L can start from 0 and end up to n minus 1. So that's it. So you have got two subshells, correct? L is equal to 0 and 1. So you have got two subshells. Those subshells are 2s and 2p. These are possible. Now, when you have n is equal to 3, the values of L are 0, 1, and 2. Right. And these corresponds to 3s, 3p, and 3d. So you can see the relation that if the value of n is equal to 1, the number of subshells is also equal to 1. When the value of n is equal to 2, the number of subshells are also equal to 2. And when the value of n is equal to 3, the values or the number of subshells are equal to 3, which means the number of subshells in any nth shell of an atom is n. You can get questions like, let's say that there is an arbitrary atom where you have to find the number of subshell in 99th shell. Okay, so the number of subshells, this is just an arbitrary question. The number of subshells in 99th shell. When nth shell is going to be n, so the answer is equal to 99. There will be 99 subshells inside 99th shell. I hope you have got the concept. Okay, next question. Among the following sets of quantum numbers, which one is not correct for the electrons present in the 4D subshell? Please note what they have given us 4D. So if it is written as 4D, you can understand that the value of n is going to be equal to 4. Let's check the options. In all the options, the value of n is given as 4. So we cannot use that to finalize the answer. Then what is given? Subshell. Subshell is notated as D. Subshell is notated as D. So we know that the values of subshells L can range from 0, 1, 2, 3, and so on. Based on this, the notations are S, P, D, and F. In the question, they have given 4D. So D corresponds to an L value of 2. So in option A, L value is given as 3, which is wrong. In all the other options, it's right. So that's it. The question is, which one is not correct? A is not correct, right? Because L cannot have a value of 3 for 4D. This corresponds to 4F. So you need not check the rest of the questions because already we have got the answer. It's an MCQ. So there will be only one answer which is correct. Okay. Next question. Again, a generalized question. The number of orbitals. The number of orbitals corresponds to M. In nth shell. So earlier the question was the relation between M and L. We found that L was found to be, or in terms of L, if, yeah, okay. So we already know that 2L plus 1 is going to be the number of orbitals, so something that you know. This is the relation between L and M. Now they are asking the relation between M and N. Okay, so let's try it out. Already from the previous questions, we know that for 1, N is equal to 1. The value of L is just 0, which corresponds to 1s orbital. You have only one orbital. Now for N is equal to 2, the value of L can be 0 and 1, correct? And this corresponds to 2s and 2p. Now 2s and 2p, we know 2s is just a single orbital. 2s is just a single orbital. 2p, this is 2s, and 2p has got 3 orbitals. Correct? So this is the S subshell. This is the P subshell. Within the P subshell, it has got 3 orbitals. We already know that, correct? Whose ML values are -1, 0, and +1. So now a total of 4. Total of 4 orbitals are there. Here there was a total of only 1 orbital. Now let's take n is equal to 3. The value of L can range from 0, 1 and 2. 0 corresponds to 3s, 1 corresponds to 3p, and 2 corresponds to 3d. And 3d, by now you know it comprises of 5 orbitals. So in total 1 plus 3, 4 plus 5, 9 orbitals. So if we can see the relation, when the value of n is equal to 1, the total number of orbitals is 1. When the value of n is equal to 2, the total number of orbitals present are 4. The value of n is equal to 3, the total number of orbitals present is equal to 9. So, if you have to relate the number of orbitals, that is related to n by n square. See, 1 square is 1, 2 square is 4, 3 square is 9, so on and so forth. So the answer is option C. Okay? Yes. Next question. Many questions. Many students have made mistake in this particular question. So mark this question as important. Read the question first and try it on your own before you watch the solution, please. So the question says, the number of electrons present in d orbital is. Now you know that when you have a d subshell, d subshell has got 5 orbitals, and each of the orbital can accommodate 2 electrons. And if you have marked your answer as 10, it is wrong. The answer is not 10. Because the question is not d subshell, the question is d orbital. The question is d orbital. Which means, see, each of these orbitals corresponds to ml values of -2, -1, 0, +1, +2. All right. So the question is how many electrons can be accommodated in a single orbital, and it is always 2. The correct answer is 2. So they have not mentioned which orbital is. It can be dxy, it can be dyz, it can be dxz, it can be dz square, or it can be dx square, y square, whatever it is. But the question is orbital. The question is the number of electrons which can be accommodated in an orbital and not the subshell. Overall, in the subshell, it can have 10 electrons, but in an orbital, it can have only 2. Okay, so please note that. Next question. Again, this is an arbitrary question. Sorry, this is not an arbitrary question. Sorry, this is a proper question. If an electron has spin quantum number of 1 by 2 and magnetic quantum number of -1, so the value of m is given as -1, it cannot be present in which of the following subshells? So let's check each of these. So in option A, the value of L would be 3, correct? We already know. So when the value of L is equal to 0, it's called S. When the value of L is equal to 1, it's called P. When value of L is equal to 2D, L is equal to 3 corresponds to F. Correct. Now they are asking in which of the following case m is equal to -1 cannot be present. Very easy. You know that the values of ml ranges from -L to +L, where each of the values have got a unit difference. So here the values of m corresponds to -3, -2, -1, 0, +1, +2, +3. So here -1 is there. So this is not the option. In D, the values of m corresponds to -2, -1, 0, +1, +2. Again, -1 is there. In option C, values of m can range from -1, 0, +1, -1 is there. But in D, the values of m can only be m is equal to 0. And hence L is equal to -1 cannot be present in option B, S subshell. Okay. Next question, very easy question. How many electrons can be described by quantum number 6? L is equal to 1. Now we know L is equal to 0, 1, 2, 3 corresponds to S, P, D, F orbitals. If L is equal to 1, it corresponds to P subshell. So the question is how many electrons can be accommodated in 6P? In 6P. So again, 6P can have 3 orbitals. The question is not orbital. The question is 6P subshell. So it can have 6 electrons. Each orbital can accommodate 2 electrons each and hence a total of 6 electrons. This is an arbitrary question. Very good question. So mark this as important, please. So question number 9 and 10 are almost the same, but please pay attention to how the question is framed. Now the question is, if a particle has 7 by 2 as its spin quantum number, now this is again an arbitrary value, the number of electrons that can be present in any orbital is. So instead of electron, I would just rephrase this question as the number of that particle that can be present in any orbital is. Because electrons have got a spin of 1 by 2, I'm not using electrons, I'll reframe it as particles. Okay. Now see, we already know that if you have any orbital, it has got electrons whose spins won't repeat. Right. For example, an orbital cannot have electrons with two same spin, 1 by 2 and 1 by 2. That is not possible. Correct? Energetically, it's not feasible. Similarly, it cannot have, or it is possible that it can have plus 1 by 2 and minus 1 by 2. So within an orbital, generally, it is said that because the electron spin is 1 by 2, it can take only two possible orientations, plus 1 by 2 and minus 1 by 2. But now you have an arbitrary orbital. You have got an arbitrary orbital where the value of spin of that particular particle, it's not electron, it's some particle, and the value of spin is 7 by 2. So each value has got a particular orientation. So now you know that if it is 1 by 2, it has got a particular orientation. If it is minus 1 by 2, it has got an opposite orientation. Similarly, if you have 7 by 2, what are the possible orientations? Within an orbital is the question. Within one orbital is the question. So what are the values? It can be 7 by 2, 5 by 2, 3 by 2, 1 by 2. And the opposite spins. Minus 7 by 2, minus 5 by 2, minus 3 by 2, minus 1 by 2. The representations won't be that easy. Okay, let's try. Let's say that this is one orientation. This is another orientation. This is my third orientation. And what can we do next? Let's say that this is another orientation. Okay. So all of these represent different orientations corresponding to the spin quantum number. Not magnetic, corresponding to the spin quantum number. So how many orientations are possible? There are 8 quantum numbers corresponding to 7 by 2, and hence the correct answer is 8. This is an arbitrary question. This is not a real life question. This question was framed so that you understand the concept. You can get such questions. Okay. Now the same question is modified. See, if a particle has 7 by 2 as its spin quantum number, the number of, I'll reframe it as that particular particle. The number of particles that can be present in any 3p subshell is 3p. Now, what is the difference in the question? In the earlier question, they asked about what are the possible orientations within an orbital, but now they are asking about the possible number of particles inside 3p subshell. So, if I have to write it down, the number of particles in an orbital that we know is 8 from the previous question. 3p subshell has got 3 orbitals. Correct. It has got 3 orbitals. It can be px, it can be py, and it can be pz. 3 orbitals. Now, corresponding to all these 3 orbitals, 8 possible orientations are possible. That means each of these orbitals can accommodate 8 particles each, and hence the final answer is 8 into 3, 24. 24 particles. Okay? Yes. So with this, we have strengthened our concepts of quantum numbers. The next session will be on the general rules like Aufbau principle, how to write the electronic configuration, the Hund's rules of maximum multiplicity, etc. And we'll be having a practice set on that also. So see you in the next session. Bye.